Here in Lesson 3, we're going to talk about the difference between observational and experimental studies. In this video, we're going to focus on observational studies, and then we'll come to experimental studies in the next video. So remember this from Lesson 2 on sampling methods. We talked about how a sample needs to be random, meaning that every member of a population has an equal chance of being selected, and the selection actually happens purely by chance. We also looked at a few of the different sampling methods. So now we get to the question, how can we best create a procedure for gathering the data? How are we going to organize our study? Well, a well thought and planned design is going to help us to eliminate as much bias as possible. Okay, so the first method is an observational study. An observational study is collected only by monitoring exactly what occurs. You either watch something as it happens and record the information, or you ask somebody about what has happened and get that information. Good example, how many students run the stop sign on the northwest corner of campus? We want to know that, so what do? We go sit at the corner and we observe. We just actually see what happens. Now, observations can be made prospectively. This is collecting the data as it occurs. So this is sitting at the corner and watching it as it happens. That would be a prospective study. Or observations can be made retrospectively, meaning you collect data after it occurs. This would be a case of, say, giving students a survey to ask them questions about some topic that we want to address. Now, there's a very important thing we have to consider at this point, and that is that we need to design a study to account for confounding variables. A confounding variable is something that could affect the data even though we're not measuring it. So, for example, let's do the stop sign on the northwest corner of campus again. We were observing people running through the stop sign. Perhaps a confounding variable will be the time of day. Could people be running the stop sign more in the morning or in the evening? Could it be how close it is to a class time? Maybe more people are going to run a stop sign if they're late for class. Another might be the time of year. During the school year, you're going to have a lot more traffic in that area. In the summer, you're going to have a lot less traffic. How will that affect everything? So confounding variables are just other variables that could affect the results if we don't account for them. Let's say that you have a study on how many Snow College students like football. And your study shows that 73% of students like to watch football games. Great. Good job. You got your study done. And then a wise friend asks you, did you compare students living on campus versus off campus? Could that confounding variable have an effect on the results? Definitely could. Another friend then asks you, did you poll the students in Richfield, on the Richfield campus of Snow College? That could definitely affect things as well. What about online students? All of these are different confounding variables that could affect the results. All right, once you have the results, you're going to divide your different variables. Let me explain it this way. When you want to compare two variables to each other, for example, you're comparing the time of day to the number of people running the stop sign, then we're going to identify one of those as an explanatory variable and the other as a response variable. The explanatory variable is the one that influences the other. It's more likely to explain why the other variable behaves the way it does. Whereas the response variable is the one that's more likely to be influenced by the other variable. For example, people running stop sign versus time of day. Is it more likely that the number of people who run the stop sign influences the time of day? Or is it more likely that the time of day influences the number of people running the stop sign? The second option is much more likely. So the time of day would be our explanatory variable, because it would explain the number of people that run stop signs, and the number of people that run stop signs would be your response variable. Another name for these would be independent variable and dependent variable. Why? Because the explanatory variable does not depend on the response variable, but the response variable does depend on the explanatory variable. Here's another example. Did you receive a vaccine, or what was your reaction to the vaccine? Those are your two variables. Is it more likely that receiving a vaccine is going to influence your reaction, or will your reaction to the vaccine influence whether you received it or not? In that case, the second option is ridiculous. You're not going to determine if you got the vaccine or not. Let me make sure I'm clear on this. Your reaction to the vaccine is not going to determine if you received it or not. It could tell you whether you did or not, but it's not going to determine if you did or not. No, instead, receiving the vaccine is more likely to determine your reaction to the vaccine. So that's a great way to determine explanatory and response variables. Which one is more likely to influence the other? Now, we have to be careful when we talk about explanatory and response variables, because when we do that, we often think, oh, there's a good association between them. Therefore, the explanatory variable causes the response variable. We've got to be very, very careful that just because there is an association, even if it's a strong association between the two variables, that does not guarantee that the relationship between the two is causal, meaning variable A does not necessarily make B happen. We only use the variables to help keep track of the variables that we suspect influence each other. Here are a couple of great examples of what I'm talking about. You see a broken gate and a duck walking through. There's a relationship. There's a broken gate and there's a duck walking through it. Therefore, the duck broke the gate. Yeah, ridiculous. I know. So just because there's a relationship doesn't mean there's a causal relationship. And then I just love this cat picture as well he found a very comfy spot, therefore he made the comfy spot. No, it's not a causation thing. It's just a correlation. So as we get deeper into statistics and we look at relationships between variables, please, please, please do not automatically assume a causal relationship. Okay, in our next video, we're going to come back and we're going to talk about experimental studies.